Hi, this is Pat Hindle with Microwave Journal. Welcome to this webinar, 3D Heterogeneous Integration, RF Microwave Millimeter Wave Solutions for Design of Phased Array Systems. It's to be given by Dr. Ian Ripke, Director of Software Solutions Engineering at Keysight Technologies, Nathan Altifer, he's Solutions Engineer at Keysight Technologies, and Edward Horn, Director of Systems Engineering at 3D Glass Solutions. In this webinar, you will learn how 3D heterogeneous integrated modules can be flexibly fabricated to accommodate multi-technology components, the EDA tools needed to correctly assemble and interconnect these mixed technology components in the 3D HI structure will be demonstrated. Then we'll cover how accurate circuit EM cosimulation can be interactively performed on any selected RF paths through the 3D HI structure without disturbing the 3D layout. And finally, they will show the 3D HI phased array module, how it can be accurately simulated for beamforming characteristics before hardware fabrication. Now I'd like to introduce our presenters. Dr. Ripke has 20 years of experience working in the simulation and design of high-frequency integrated circuits, including several technical publications and patents. In his current role, he is a director of Keysight's EDA Solutions Engineering and Services team in the Americas. He holds a BSEE from Lafayette College and PhD from Electrical Engineering from Cornell University. And Nathan, he works with and coordinates applications engineering teams to ensure customers derive maximum value from their Keysight EDA design tools and design flows. He monitors and manages all the technical account activities, including training, services, support, and tool evaluations. And he collaborates with customers, subject matter experts, and R&D to develop new design capabilities and design flows that address customers' evolving and complex design requirements. And Edward is Director of Systems Engineering at 3DGS and is responsible for helping customers implement their designs using their technology. He brings 20 years of experience leading technical teams in RF design, characterization, modeling, and manufacturing. At Paratech Microwave, he designed the tunable RF chip and the first ever antenna tuner inside a cell phone, which now is an industry standard, leading to the acquisition by BlackBerry. He had other positions, and he holds a BS and MS degrees in electrical engineering from University of Waterloo. So at this point, I will turn the presentation over to Dr. Ripke.
Welcome everyone to our presentation today on 3D heterogeneous integration solutions for design of phased array systems. This presentation is brought to you jointly by Keysight and 3D Glass Solutions. Your presenters today will be myself, Dr. Ian Ripke, our solutions engineer, Nathan Altifer, and our director of systems engineering from 3D Glass Solutions, Ed Horn. So, we've heard a lot about the need for 3D assembly and for heterogeneous technology integration, but what's driving this? Well, it's really what I like to call more than more meets swap C. We want to build denser, more flexible assemblies. We want to be able to use the best-in-class ICs for any given application. And we want to be able to tackle new applications that might require reduced footprints or be able to pack just more capabilities into a standard footprint. Where we can't go out on the sides with chip sizing, we're going to go up with 3D heterogeneous integration. The outline of our presentation today will be an overview of 3D HI glass RF front-end modules by Ed Horn from 3D Glass. We'll then jump into the design flow for the assembly and analysis of 3D heterogeneous integration technologies brought to you by Nate Altifer from Keysight. And then finally, we'll conclude with how you bring this together into a phased array system design with 3D HI by myself, Ian Ripke from Keysight.
My name is Edward Horn, Director of Systems Engineering at 3D Glass Solutions, and today we're going to be talking about 3D HI glass RF front-end modules. So 3D HI is a technique to stack multiple chips on top of each other to reduce your XY footprint by going up into the vertical direction. Phased arrays are a great application for 3D HI as you have a fixed antenna size based on your lambda over 2 spacing between different antennas. So if you have a lot of functionality in your RF front end that you need to worry about, you need to be able to stack and go in the vertical direction to fit everything underneath your tile. At 3D Glass, we have worked on a number of different phased array 3D HI modules, and the best way to kind of describe what we're able to do is to go through an example. And today we're going to be talking about the MFM1 module. It's a 6 to 12 gigahertz half duplex RF front end. It's a simple example. I like this one. This one's also nice that it has measured results, so we can compare simulation in RF Pro to measured results on the PCB that you see over here on the right, which is de-embedded to the module reference plane. So this design itself is more of a front-end module. For phased arrays, we're also able to implement beamforming ICs and integrated antennas. So 3D Glass, we are a glass-based foundry located in Albuquerque, New Mexico. Most of our products kind of fit into two categories, which are RF integrated passives and RF interposers. Everything is based on a photosensitive glass material called Apex. As most of you probably know, glass is a great RF material for low loss interconnects and high frequency applications, but it's difficult to deal with in manufacturing. We've been able to solve those manufacturing challenges by this photosensitive glass material. So if you take a glass substrate in our fab and expose it to UV light and heat it up, those regions that were exposed are going to turn into a ceramic form. And that is important because you can wet etch that ceramic. So it doesn't matter if you have 2 vias or 22,000 vias in your substrate, they all get cleared out at the same time. So it's quick and cost effective. The etch profile of this wet etch is also very anisotropic. So we're able to hit 89-degree sidewall angles and 8:1 aspect ratios. So that's really important. We're able to create dense routing and compact low-loss RF structures. So for an integrated passive device like an inductor, we're able to create very high Qs. Sometimes they can hit as high as 100 below 6 gigahertz. So if you have an RF circuit, we can probably make it in a smaller form factor and lower insertion loss. The rest of our fabrication, it just involves standard semiconductor processing. So we'll have a redistribution of layer of copper on top of the glass and on the bottom of the glass, and then fully plated vias all the way through the substrate. So those are technologies that 3D Glass uses. We also build substrate integrated waveguides, antennas, photonics, microfluidics, quantum, and more. 3D HI is kind of the whole kitchen sink on top of it. You can mix and match different glass technologies together on different layers and then stack them up vertically on top of each other. So again, we are a foundry. We help customers build devices that typically kind of solve miniaturization and integration challenges at high frequency. So 3D HI, for phased arrays, the design of these systems are becoming more complicated, especially as we go higher in frequency. As the size of the tiles get reduced, it becomes more and more challenged to fit more and more functionality underneath a specific radiating antenna element. So this is where 3D HI comes in to pack more than more, as Ian said, and you can mix and match the different technology implementations to target the different functionality that you need to achieve. So you can optimize for size or cost or power and yield depending on your different technologies. And we just stack them on top of each other using different glass substrates provided by 3D Glass. And then the glass itself is stacked on top of each other using solder ball or nano silver type glass connections. So in this case, we're able to then get very small, highly integrated, complete phased arrays in a single SIP module. This can then be assembled on to the customer's next level assembly or PCB. These are all the different 3D HI capabilities that customers are asking 3D Glass for. This kind of shows this cartoon of all the different types of functionality that we need to be able to handle for 3D HI modules. For phased array modules, the two important ones we'll be talking about today are focusing on this design of MFM1 are what we call cavities. We've got two different flavors, a picture frame and a window frame. A picture frame cavity is using the same wet etch technique that I mentioned that we use for vias, as you can see them all the way through the glass substrates. We can repeat that process and create any shaped cavity to create room for any of these active or passive components that we want to integrate inside the glass substrate. So stacking glass layers is great, but you need to be able to create this breathing room for these components inside the 3D HI module. So this number 3 is a window frame. So we'll clear out the metal and the glass on both sides of the substrate. And over here on the left, the picture frame, we still include the metallization layer on one side of the glass. Typically, we use this on the bottom or top layer of a module if we want to have, or if we need a ground plane. So these are the two that we're going to be using today. Also for phased arrays, it's important in other designs where we want to include an integrated antenna in package. Again, not today, but other designs we have implemented successfully. And another thing for getting heat out of 3D-HI modules, we use dense arrays of thermal vias under any heat generating element. So glass is not a good thermal insulator, but copper is a terrific one. So we have different types of thermal solutions for getting heat out of these complicated modules. 3D glass, again, as I mentioned, has different glass technologies available for different types of applications. But for 3D-HI, you can mix and match and pick your favorite to suit your particular application. Over here on the right is an example of a 7-layer 3D-HI module. It looks like a bookshelf here. There are dozens of active and passive components integrated inside. They fit inside those cavities that we just looked at in the previous slide. And in this case, the customer was able to reduce the swap C by over 95%. They came to us with a PCB type of implementation, and using a glass SIP module, they were able to fit this inside of their phased array, a complete L-band transceiver using our 3D-HI technology available at 3D Labs. This is a zoomed in picture of the module on the previous slide. So stacking glass sounds great. How do you actually go ahead and implement that? Typically, our 3D-HI modules are organized into pairs of glass layers. So over here on the right, I'm showing two different glass layers that are mounted on top of each other. So these two layers, one is a RF layer, we call it at 3D Glass, where we'll integrate and assemble all the different active and passive components onto the bottom glass layer. We also have a matching mechanical layer, you can see above, that has the cavities included over the components on the RF layer below. There's also an array of solder balls that provide the glass-to-glass connection between glass layers. Now, this is a pair of glass layers, and we've repeated this process 3 more times to create this 7-layer glass SIP module with the final lid layer on the top. This is a good place to kind of look at the TGVs that we talked about earlier. So the vias that make a connection between the top side and the back side of the glass substrate, you can get a good view of here. You can see the very high aspect ratio, and they're filled completely with copper. These are not placed at minimum spacing for a ground plane connection in between two glass layers. We don't want to have it too dense of an array, but we can actually put these at minimum spacing at twice the diameter. So if this is a 40 micron TGV, we can place them as close to 80 microns center to center. These are probably closer to 300 microns. This is the same approach we'll be using in the MFM module, except that we are only going to be using 4 glass layers in this particular example. So, component assembly. This is sort of a fundamental key feature for any 3D-HI module. Our glass substrates use a copper redistribution layer on the top side and the back side of the wafer, and it's covered with a solder mask material. Inside the solder mask openings, we will also include a standard any-pick finish, which is assembly friendly for flip chip, for wire bond, for solder stencil. We've been able to handle any sort of customer assembly requests. A key part of any of these assemblies is to be able to handle challenging reliability requirements, and we've been able to temp cycle all of these different assembly options that I just mentioned and put through some other reliability testing with success. A key reason for that is the CTE of our glass is 8.5 ppm per degree C, and that is half of what copper is and double what silicon is. So the CTE matching to copper gives us good reliability. Glass is also very well suited for challenging environments. We have glass that has been in space, that has been flown on the F-35, that has handled cryogenic temperatures. We have other glass that is working at above 600 degrees C. In fact, glass that's been shot out of a cannon. So glass is, well suited for challenging environments. Over here, you'll be able to see a few pictures of the cavities in more detail that we talked about in the previous slides. Our glass is photodefinable and designed using a mask. We're able to create any shaped cavity that you want. So that gives us some flexibility to optimize the design of the 3D-HI module to fit components in very tight spaces and in challenging geometries, as you can see here. Another key feature about these cavities is we can line the perimeter of these cavities with vias that are, again, plated full with copper, and we're able to create mini Faraday cages where you have ground literally on all four sides of the cavity, as well as on top and on bottom with ground planes on the neighboring glass layers. So that enables very good isolation between neighboring cavities. So if you have a noisy transmitter, you're able to place it in close proximity to a sensitive receiver. Often these desense challenges could limit how close you place these components together, not so much the mechanical and assembly reasons, but from just interference alone. But using these unique cavities that are grounded on all six sides, we're able to solve challenging coexistence and interference solutions. So not on these type of 3D-HI modules, but we also have substrate integrated waveguide components, which are used to create higher frequency millimeter wave type filters. And if we have two adjacent waveguides, we're able to measure isolation between those waveguides in excess of 60 dB. So many of our customers take advantage of these cavities, and they come for free. They're not an additional feature. It's just how you design the layout of the vias around the cavities that you see here. So those are the technology details of how we build glass substrates and how we stack them together. How do we implement these inside of ADS? We built a PDK with our friends at Keysight. Here I'm showing two different stack-ups. One is a simple 1+1 stack-ups in the 3D-GS nomenclature. That means one redistribution layer on the top side, M2F, and another redistribution layer on the back side, M2B. These are connected together with a through glass via, but through the substrate, and an optional cavity layer, which we'll use on the mechanical layers to create space for the components on the layers assembled below or above. Finally, we've got two die attached layers, bump on the front side, bump on the back side, and solder mask on the front and back as well. So this is sort of our baseline substrate definition we'll use for 3D-HI implementations. If you're just interested in doing a single glass layer and maybe designing a bandpass filter or Valin or your favorite RF circuit, we will also implement MIM capacitors and thin film resistors. And if you're doing more advanced packaging type applications and need multiple redistribution layers, we can also have additional layers M3F, M4F on the front side and two more on the back side. So we would call this one a 3+3 stack up at 3D Glass. For single glass layers looking at RF passive devices, we have a number of components that are parameterized in terms of their layouts. So you can change the parameters and the layouts will update. We also have equivalent circuits that will model all the parasitics and losses and non-ideal effects. So you'll have much more optimization capability at the circuit level before starting your EM simulations. Over here on the left is a typical product that one of our customers designed. It is a bandpass filter from 3 to 5 gigahertz. You can see the 3D spiral inductors in the substrate, along with the BGA footprint solder balls. This will be flip chipped over onto a PCB and reflowed. The other main single layer glass design that we do for most customers are interposers. And here we're typically using more redistribution layers rather than passive components, although you can do both. We're able to do the routing inside ADS with substrate, pad stack, and via definitions. We're able to route and keep net lists and make routing through multiple RDL layers quick and easy. Here's a picture of a particular interposer that was made with 3 layers of metal on the top side and 3 metal layers on the back side. And there was multiple chips that were flip chip assembled on top of this substrate. And here's a zoomed in X-ray view of one of the areas on side of that chip. And I like this picture because it shows the TGVs in the black circles that you see here. So you can see how straight the sidewalls are and how tight and how close you can place these vias together. So this is the unique technology that 3D Glass brings to the table for both the integrated passive devices and for packaging applications as well. And then we stack those in glass layers together for all the 3D-HI stuff that we're talking about today. So that's single layers of glass. How do we design for 3D-HI applications when we stack multiple layers of glass together? We can't be making a separate PDK for all the different types of stack-ups that we can conceive because there's just too many variables. So these are the key challenges that we're trying to solve in setting up PDK for 3DHI, and with our friends at Keysight, we're able to come up with this solution. So these were the things that we were able to figure out, the key requirements. So the PDK needs to be stackable. The designers that have the PDK need to have the flexibility to change the number of glass layers they need. Maybe I can design this one in 6 layers, or if I do a really tight layout, maybe I can do it in 4. So that ability to be able to explore that design space is key. Swappable. What I mean about that is earlier we showed all the different types of glass technologies that we're able to create, and to be able to switch an antenna layer for a microfluidic layer, for a routing layer, for an IPD layer. The designer again needs that flexibility to pick the correct technology for the correct requirement. Or maybe they just want to change the glass thickness layer. Integration, this is the key one here. So the customer who's designing their chip and using a glass module needs to be able to easily integrate their IC inside of this complicated stacked glass module. And Smart Mount is the key technology to be able to implement all this die stacking to glass, and then the second phase, which is the glass-to-glass stacking to create the full 3DHI modules. Finally, they might also want to do their chip design and package design at the same time. So this chip and package cosimulation is a further improvement to be able to do both at the same time. Instead of designing your chip and then thinking about package down the road, if you optimize both at the same time, you're going to get even better performance. So maybe this is something we're doing with customers on, their second or third project with 3D glass. But this is a key thing for us where we can really take full advantage of 3DHI applications. Finally, design for manufacturing is very critical. At the end of the day, with whatever you design, we need to be able to build it at 3D glass. So customers will have to be able to run a DRC and export a GDS file to send to us for a tape out. So we talked about glass stacking and RF applications. That sounds great, but if you need to be able to do this at high frequency. So if you're stacking multiple glass layers together, we need to be able to have controlled impedance, low loss transitions between those glass layers. So if you could only put a chip on a single glass layer and it always had to be on the bottom floor, that makes it a lot less interesting. But in this case, we're talking about a stacked 4-layer glass module. In this case here, the blue is the top metal layer, green is the bottom metal layer, and the pink cylinders are the through glass vias that are filled with copper. In this case, this is a vertical coax connection between 4 glass layers that has better than 20 dB return loss up to 20 gigahertz. So both the transition in the glass layer and the thinner air gap between the glass layers were able to get good low loss connections at high frequencies. This is a key building block for doing any type of phased array or other RF SIP module. Finally, getting into the application itself, the MFM1 module that we talked about. So again, this is a half duplex TX and RX amplification module. We've got a power amplifier and a low noise amplifier that are switched between 2 switches on the input and the output. The customer wanted to put a thermal interface on the top side of this module. So for that reason, we put the power amplifier and the LNA on the bottom side of the top glass layer. And then the third glass layer has cavities to create room for the PA and the LNA. And those are wire bonded down to the bottom side of the top glass layer. Finally, there are 2 single pole double throw switches, which are flip chip assembled to the bottom side of the second glass layer. And again, there are cavities in the bottom glass layer to create room for those switches. In this case, there's a window frame cavity on the third glass layer and what we call a picture frame cavity on the first glass layer. So glass layer number 1 also has a LGA footprint that can be assembled onto a customer PCB with a solder stencil. And over here on the right is just a simplified cartoon of the cross-section of this module in ADS using Smart Mount. So this is just a simplified view with just a few vias for visualization purposes, but you can see the PA and the LNA along with the associated wire bonds in the cavity of the third layer, and then the switches that are in the cavity of the first layer. The real design has thousands of vias. This is just a quick view for illustration purposes. This is the schematic with the 2 switches on the second glass layer and the 2 amplifiers on the fourth glass layer with just vertical pass-throughs on glass layer 3 and glass layer 1. This is what the layout looks like for each of the glass layers. Starting on the left at glass layer 1, Moving over to glass layer 2, 3, and 4 on the right-hand side, where we have the PA and the LNA mounted to the bottom side of the top glass layer. And simulating each of these individual layers by themselves is not sufficient. We need to be able to assemble these glass layers together and provide EM simulations of the full stack together. Key way to look at this is these transmission lines on glass layer 2, they will couple to the ground layers on glass layer 1. So all those electromagnetic effects need to be incorporated into a full module RF Pro simulation. So 1 plus 1 doesn't always equal 2 here. And Smart Mount is the key technology to be able to implement all this die stacking to glass, and then the second phase, which is the glass-to-glass stacking to create the full 3D HI modules. This is a picture of the 2 RF layers, glass layer 2 with the 2 RF switches, and glass layer 4 with the 2 amplifiers and 10 discrete capacitors. The orange is the solder mask, and the little circle openings are the openings that we will use the solder balls for the glass-to-glass connection. The lighter yellow color is the exposed copper in the solder mask openings. Finally, here is a picture of the fully assembled MFM module. It's a bit of a busy picture, but the larger circles you see here in the X-ray photo show the solder ball connections between the neighboring glass layers. And the smaller dark circles are the TGV via's individual glass layers. So you can see the LNA on the top, the PA on the bottom, and some of the other discrete caps you see here. So X-ray is a very useful tool for us as we're confirming that assembly has been done properly and any troubleshooting that might come up along the way. Finally, this module was assembled onto a PCB and characterized up to 20 gigahertz. And Nate's going to show you how to implement these details in ADS and compare the simulation results to the measure results from the board that you see here. Finally, this is just how everything is organized inside of ADS in terms of the library configurations on how to do the assembly. The recommended way, there's different ways to put this 3D puzzle together. The recommended approach is to do each individual glass layer in its own separate library, along with the separate component assembly for the switches and amplifiers in each individual library. Those components are located in here, MFM1_ICs. And then you do the sort of final module assembly in a parent library that I've called here 3DHI demo_lib. So that sort of hierarchical approach suits us, is the best we've recommended to complete these 3DHI modules. And finally, the PDK, if you're going to design a single glass layer or stack glass layer modules, everything is located here in the 3D glass PDK. So with that, I'll hand it over to Nate, who's going to do a live demo and walk you through some of the important details on how to set up one of these modules in ADS.
Thank you, Ed. I'm going to dive a little bit deeper into the flow and in how this is built using ADS. So everything is going higher in frequency. The bandwidths are getting larger. All this is driving higher spectral components into the designs that people have to account for and handle. And one of the big problems you get into with these higher frequencies that are being brought in is parasitics and interconnect, for example, that people used to be able to ignore can no longer be ignored. These now become very important parameters to the design and have to be accounted for. And we're not just talking about interconnect in a chip, but interconnect between chips when you're going through a board or interposer. So there's a real need to bring all this together in a common design environment. Another problem we run into when we start looking at these higher frequencies is that basically everything becomes an antenna. And so when you start doing things like phased array designs, and you have the phased array sitting on top of all these different chips, operate these higher frequencies, you have components inside your designs now that may be radiating that you don't expect them to radiate, or you weren't considering them radiating, that may interfere with the performance of your design. So really, going back to what you said, 1 + 1 does not always equal 2. You really have to put all this together and analyze it in one environment so that you can account for all the effects between the different designs that are operating together. The problem you get into with trying to do that type of design flow where you have this heterogeneous design is that it just gets complicated, especially when you have lots of different tools that are being used. Bringing everything together into one environment becomes very, very hard. You're typically translating designs between different formats. You're bringing in measure data files. You may have 10 port data, you may have 500 port data, and that all has to be connected and wired up, and it just becomes incredibly tedious and very, very error prone, and the tools have to be able to handle that. When you do get into a flow where you can handle that, it really simplifies things quite nicely. When you have designs, multiple chips and maybe multiple packages all working together, you now have this ability to do co-design built into your design flow. And that's important when you have this type of module design you have to work with. You also have the ability now to plug in tools and models where they make sense, right? You can partition your design up in certain ways. And when you have a design flow that has the automation and the intelligence built in to do that, it becomes very, very easy. And that's what I'll talk about in just a few minutes here. Now, the other thing that this really helps simplify is you can find problems early on in your design cycle and mitigate them before going to tape out and testing and measurement and then going back and iterating, through another spin. So this can significantly reduce the number of spins as well as design cycle time. The two big problems you run into with doing this type of 3D HI design, at first, it's just very complicated, combining different technologies together into one design. A lot of times you have scaling things going on. You have designs that may be done in microns being combined with packages done in millimeters being put on boards, being designed in mils. You have different database resolutions between these three environments. And when you start just copying files together, things start expanding or shrinking drastically. And having a tool that understands database resolutions along with different units and can scale your designs appropriately, so when you combine them, you have an actual representative of your final product. That's one big aspect that not many tools can do that. Our solution to this is Smart Mount, and I'll demonstrate this live. But as you talked about, this is fairly unique, and it's just a simple drag and drop to combine your designs. You can change layers on the fly, change how they're mounted, and again, I'll demo this live in just a couple minutes here. The second problem you start to get into with these heterogeneous design flows is you have the ability now to build these very complex problems, and now you have to solve it. And these are very big problems. That you need a lot of compute power. You need resources that you can use to solve these problems. Sometimes this is clusters, sometimes this is cloud computing, but having the ability now to do all that is essential for these types of problems. Our solution to this is built into our RF Pro. This is our EM platform. The RF Pro is very scalable. It works down at very simple design level. You can use this for input matching networks all the way up to full chip, all the way up to full 3D HI designs. So it's very scalable. One of the big things we wanted to really focus on with this too, once you start getting into all these different technologies, is it's important that you work on the manufacturing layout. If you have to start making copies of your layout so that you can EM them, that all of a sudden becomes very, very tedious. And you start doing that across multiple technologies, boards, chips. It quickly creates a vast array of different designs that you have to manage and try to keep in sync. And then that becomes very, very hard to do. So working directly on the manufacturing layout was a key objective of this flow. So what does that mean? First of all, automatic cosimulation is automatically supported in this flow. That means if you have active devices anywhere in your hierarchy, RF Pro will automatically take those active devices out, put in ports where they connect, EM the passives around that, and then at the end, recombine that EM data with those active devices. The same is true if you have SMD components. You're downloading parts from a vendor website. You don't have the layout, but you have the model. You can go ahead and set that all up in your ADS layout environment, bring that into RF Pro, and it will automatically pull out those SMD components and put in the model and co-simulate at the end for you. So you're running on your manufacturing layout. And this is a very common problem that people run into. The example that we're walking through with this MFM module is using components from analog devices. And you can download these components directly off their website, which is exactly what we did. But you don't have access to the layouts for the amplifiers and switches. it's nice to have it. The more layout you have, the more EM you can do, and you can better account for the effects of the layout between the different technologies. But if you don't have the layout, which is most people don't, you don't need it. You can have RF Pro automatically plug in the models and set that up for you. And I'll show all this at the end. The other thing that we do to make sure that you work in the manufacturing layout, a lot of times you have a problem that's just way too big. You don't have access to the compute resources you need. So what we have a capability called mesh domain optimization, which will allow you to just analyze specific nets or specific areas of your design. And these nets can start at the bottom of the design at the board level, go up through the vias and bond wires, whatever, up into a package, up into chips or cross chips. It will extract the entire net out of the design for you. Do a mesh domain optimization, which is a virtual cookie cut around that structure that you've identified, and just do an EM analysis on that structure. And if you have actives or SMD components in there, it'll do that whole cosimulation thing just with that mesh domain optimization that you've done. I really want to emphasize, work on your manufacturing layout. No intermediate or copies of layouts are needed with this flow. The big advantage that you get into with being able to do this automatic cosimulation is that typically when you're done with EMing these designs and you have other parts that have to get wired back in, these active devices, you can have easily up to 100, 200. I have customers that go up to 500 ports when they're doing their EM analysis, and then they have to wire all that back up. That is incredibly tedious and, again, incredibly error prone. So being able to do all this, which the touch of a button, is incredibly helpful. Some of the other things we have built into this flow are being able to automatically assess manufacturing impairments without doing any layout parameterization at all. RF Pro can statistically manipulate the mesh to look at the effects of over-etching or under-etching that happens in the processing. What happens if you have mask registration problems? Your X and your Y don't quite line up. How does that impact your vias? How does that impact the signal paths? So you can set all this up in RF Pro and have it automatically do that for you. And one of the big things we focused on is having intelligent EM settings built into RF Pro so that you have confidence in your EM results. And we have plenty of benchmarks we can get into if there's questions. So with that, I'm going to stop the slides and I'm going to go right to demo. And this is going to be working on this design, this MFM one design that Ed was talking about. I'm using ADS. I have the same design that Ed has. Here's our simple schematic. We have a couple switches that are going into an LNA and a PA, a very simple design. We look at the simulated versus measured for just this simple schematic. You can see we have a little bit of discrepancy, especially at the lower frequencies. It's for the PA, for the LNA, things line up okay at the low frequencies, but you can see the divergence as they start to get higher and higher in frequency. And this is where being able to do this full 3D HI analysis becomes very, very important. So you can see the degrading effects of the environment that these chips are working in. So with that, let's jump into the actual design and go from this idealized schematic to the actual design. This is the full layout that's been assembled, and there's a couple different components to this. There is the board level, which is just these traces coming in, and this board was done in millimeters, I believe. On top of that is this full glass structure. So let me highlight this very quickly by just showing at this level, this top level design where we're running our EM simulations. If I pull up the substrate for this, so this is the substrate, and you can see this isn't showing the full substrate. This is just the board. It's a simple metal with a via down to ground. And this is the beauty of Smart Mount, because if I go in here now and I select this structure, you can see through the Smart Mount editor, this structure is this full 4-layer assembly that's just smart mounted directly on top of the con layer. And it's very easy to go in here and change how this is stacked. If I wanted to make this flip chip or whatever, I can change it all with just a simple couple of right clicks with the mouse. And if I descend down into it and show the substrate again, now we have a very different substrate. So this is building up the entire design. I combined all 4 layers that Ed showed into one layout, and that is being represented here. So I manually created this stack up. This, whether you do it smart mounting each layer on top of each other or go through the steps that I did to combine it, you get the exact same result. But this just shows with, I think, a little bit more clarity just how complex this can be. In this structure, there are several different metals like this M2F4, M2B4, M2F3, M2B3, M2F2, M2B2. These are the layers that we're using the smart mount now, those switches and amplifiers into this full 3D layout. And let me just highlight that. And it shows in the smart mount instance editor exactly how this is set up. And again, I can right click at any time and change how these are stacked, what layer they're mounted to, and the orientation, whether this is flip chip or a traditional bond wire type design. In addition to being able to specify that, we have built-in components for handling the bond wire. So all this is assembled natively inside of ADS layout. I've defined what layers I smart mount the amplifiers and the switches onto, and then I add in these bond wires. And if I go to my navigator, you can see we have several bond wires that are set up. I've highlighted all the bond wires. These bond wires, by the way, are very configurable. These are set to inherit a shape, and you can define any shape you want and show you how this is set up for the bond wires. So we specify all the different vertices in this bond wire in this table, and you can specify angles, you can specify lengths as a proportion or lengths as a total distance, and it's very easy to also parameterize this. So you can now set up parameterized bond wires and sweep loop heights and things like that. And when all is said and done and built, I'll just bring up RF Pro. First, if I go into our wireframe mode, it makes it a little bit easier to see everything that's going on. And immediately you can see all the different vias, solder balls, and things like that that are in this design between all the different layers. Here, I can highlight PA, LNA, two switches. These components, I am telling RF Pro not to EM these, but to use a circuit model instead, right here. And this is kind of neat, so I'll quickly just break this down. This one big block here, this 22-port S-primer file, this is the EM results that were generated by RF Pro. So all the passives between the switches, amplifiers, capacitors, that's all in this EM block right here. And then you can see that each wire coming off this has a really ugly name, but this is how it connects to all the components that we did not EM, all those capacitors, the amplifiers and switches that we don't have the layouts for. We just did a cosimulation. All these are connected by name to these components. It doesn't matter if it's 22 ports or 500 ports, it's automatically wired and it's wired correctly. This is the EM and the circuit model co-simulated together. So you can see the results line up much better with the measure data from the ideal. And in the case of the LNA, where we go higher in frequency, the measurements start to drift from the ideal. You can see that our co-simulation results with EM and the circuit models now track much, much better with the measured data. I also threw in here the isolation, and I think this is a testament to the 3D glass processing. You got pretty good isolation. This matches up really, really well, even with the more idealized schematic results. But it's just a very nice confirmation of this design flow, being able to do the assembly and the analysis all inside of RF Pro. So as you can see, I wanted to just look at one trace. This was just the input trace into this module. And I turned on mesh domain optimization, and you can see that it did this kind of virtual cookie cut around this net. And this highlights two things. First, you can use the production layout. It doesn't matter if there's active devices, if there's component models and things like that. This works with that kind of setup as well. It works with hierarchy. It works with different technologies. And you don't have to create a different version of your layout or copies of your layout in order to make this happen. Cookie cutting is a fairly common practice that a lot of people do. But looking at this, the way that it extended the mesh out beyond just this net, I don't think many people would probably have actually cookie cut this far out. But the algorithms that are being used to determine how far out the mesh has to go are very important here. A lot of times when people do cookie cut, the biggest problem they run into is they've cut too close. They've cut the ground plane too close to their signal, and you get these artificial resonances being predicted that don't actually exist. So with this mesh domain optimization, that takes care of that for you. You don't have to worry about it. So in summary, we have some nice capabilities with Smart Mount and RF Pro being able to analyze these full structures. And the next step, of course, would be to take this and now bring this into a full phased array application. And I will let Ian take it from here to discuss that.
Thank you, Nate, for that excellent demonstration of how to use ADS for 3D heterogeneous integration design using 3D Glass's PDK for ADS. So So far, we've seen how to get very accurate simulation level details with electromagnetic analysis for multiple chips and passives integrated into the 3D glass technology stack. But how do we take this into the bigger picture of a larger system design, such as a phased array? What we want to do here is we want to create a behavioral model of all of that excellent work that Nate and Ed just did, but use it in as accurate of a representation of our phased array system as possible. This is how we're going to create a digital twin representation of this system. And that's going to consist of a number of different components. Our front end module is shown here. That's our 3D glass structure with our transmit and receive. We're also going to include a beamformer IC so that we can implement the taper and phase adjustments. And then we're going to incorporate an antenna pattern to this as well, which we're going to use as accurate of a representation as possible. Starting with that antenna, what we're doing here is creating a notional 4x4 or 16 element array, again, using the 3D glass technology. So we've used one of their structures to represent a multiple stack antenna, so basically a dual polarized patch. And we're going to use this analysis to build this into the larger array structure. This can be done inside of RF Pro again with the same workflow that Nate just demonstrated. And what this is going to do is create a multi-port excitation or a far field I/O pattern that we call from inside of RF Pro. And it's going to start with an individual excitation of each patch that'll include all of the nearby coupled structures. So by doing a multi-port excitation and combining all of those individual patterns on the left, we get the actual beam pattern at bore site for that phased array shown on the right. And here what we can do is we can look at bringing those far field I/O pattern behaviors as well as the S parameters, all that coupling information into our system view, system level simulation tool. What we have on the right is going to be the actual directivity versus theta for the EM analysis. And on the left is the reproduction of that exact same data inside of system view. This gives us a very good starting point with an antenna that we can now match to that circuit work that was done in the previous section. So showing that, what we can do here is take the electromagnetic data in addition to the chip data. Again, we had the S parameters, or in this case, we're using a library of parameters called sys parameters. They're provided by analog devices, and they're going to give behaviors of the PAs, the LNA, and the switch over temperature, frequency, operating point, all of those different characteristics for use inside of system view. What's unique here is we're going to reuse the electromagnetic simulations that Nate did, and we're going to select the specific nets that are the connections between all of these different circuit components. Once we've done that, we can actually extract the individual S parameters and load those directly into system view using a feature called EM Link. When that's done, what we can do is simulate the overall circuit response with those electromagnetic effects. And we can see on the right very similar responses to what Nate showed with the adjustments between the ideal schematic and then the schematic including the electromagnetic simulation. So we can be very confident now that we've imported as accurate of a system level model as possible for the front-end module in the 3D glass technology. So adding in a beamformer IC, in this case, we're going to be using the Analog Devices 8R1000 beamformer, which works in the same frequency range as the transmit and receive module that was just developed. And you can see a number of different parameters that are available in this model. This model is provided by Analog Devices, and it incorporates a number of different settings representative of the different controls and configurations of the beamformer IC. So having this accurate system level model for the beamformer gives us the ability to, again, extract a kind of measurement-based behavioral model that's verified and validated and provided by the manufacturer. So combining all of this together, it's going to let us create a transmit and receive path, which includes our phased array antenna, all of the S parameter models captured here for that, as well as the actual beam patterns. It's going to be a very accurate front-end module transmit and receive path, and then a measurement-based, highly accurate behavioral model of the beamformer IC. With all of these together, we're creating a system-level analysis of this phased array using extremely high fidelity simulation and measurement based models that come from ADS or from our Keysight test equipment. So in this case, we just look at an example of how we've brought all these different designs together as subcomponents and models in this analysis. Inside of each of those blocks for the front end module and beamformer are the more complicated circuits that we showed in the previous slides. And with this, we can very easily model the signal power, the signal frequency, and look at the overall response of our phased array, all by using those highly integrated analyses that we did earlier. And when we look to compare the beam pattern, we have the example on the bottom is our actual electromagnetic simulation. The graphs on the top show the results coming out in system view, and we can see excellent correlation between the azimuth and elevation scans in this case. What this is going to let us do is a system designer could create a highly idealized behavioral model to begin with. And as decisions are made on what chips to use or designs are completed for individual ICs, all of that information can be brought back into the design to refine the model and give you better fidelity. And ultimately, what makes this a true digital twin is once all the components are actually built and measured, we can do correlations then to make sure that we have measured data feeding those models, and we've evolved this now to represent the actual system that's been implemented. And this is just one final example here of being able to plot all of those different beam scan angles for elevations from -60 to +60 in 15-degree steps. This gives us a very fast, very accurate way to predict what our phased array system is going to operate, again, with bringing in all of the models and measured data that were used throughout this design process. The key here is choosing how to partition our designs. We wouldn't want to do all 16 channels of that previous design in a full electromagnetic analysis, maybe once as a final validation. But in the design process, it's not possible to run those simulations and iterate on your designs quickly. So by using system level representations of the phased array, but incorporating the accurate models of the individual components, you get the best of both worlds, and you can create very accurate digital twins of your systems while still incorporating all of the unique capabilities of 3D HI. So in conclusion, to wrap up today's presentation, what we have here is you've seen that the technologies and the tools are here to make 3D HI a reality. We saw the unique stacked glass capabilities that 3D glass provides for all kinds of different applications and conditions. You saw how a design kit for that same technology in ADS could be incorporated along with behavioral models of circuits or even actual circuit level models if you're doing the circuit design yourselves, and pulled together inside of the RF Pro tool to do a full hybrid electromagnetic and circuit simulation. And finally, we talked about how partitioning your design, but keeping the accuracy of those models, allows you to very quickly extrapolate those individual 3D HI stacks into a complete phased array system, giving you all the capabilities of 3D HI for phased array applications. So thank you very much for attending our session today. We'll be taking questions as well as providing resources for further information very shortly.
Great job on the presentation, guys.